Hi everyone, I'm Vimal, a researcher at the Human Computer Interaction Institute at Carnegie Mellon University. And today I'm super excited to be presenting IMUPoser, full body pose estimation using IMUs in phones, watches, and earbuds. This work was done with my awesome collaborators Riko Arakawa and Karan Ahuja, as well as my amazing advisors Mayank Goyal and Chris Harrison. So, tracking body pose on the go could have powerful uses in rehabilitation, fitness, mobile gaming, and context aware virtual assistants. But contemporary full body motion capture either requires specialized rooms and equipment or arrays of special sensors worn all over the body, neither of which is really attractive to end users. Meanwhile, we already carry a bunch of motion IMU sensors with us every day, found in smartphones, smartwatches, and wireless earbuds. And so instead, in this work, we explore the efficacy of using IMUs found in these commodity devices, such as smartphones and smartwatches, for full body pose estimation. And before we get started, here's a quick video demo. So on the left over here, you see our system running completely live on our laptop. And as input, we provide data from our smartwatch and our smartphone. And these are most importantly worn in sort of day-to-day locations on the wrist and in the pocket. And right now you see me walking around, and soon you'll also be able to see me performing a couple of squats and also jumping jacks. So there's been a lot of work done in tracking pose with external sensors. For example, commercial systems like the Vicon and OptiTrack use specialized IR cameras and markers to track pose at millimeter level accuracy. However, these systems cost upwards of tens of thousands of dollars and are usually out of reach for most consumers. Camera and depth-based systems like the Kinect provide a good balance between cost and functionality, but they are generally immobile. And similarly, specialized hardware exists to track users in VR and AR, such as the HTC Vive trackers. But overall, these systems are either too expensive, too bulky, or privacy invasive, and most importantly, you can only move within a certain space in which the system is set up. And that really is a hindrance to tracking full body pose on the go. On the other hand, researchers have also studied body capture using body-worn sensors, ranging from cameras, depth sensors, worn biosensing, and also IMUs. As early as 2011, researchers were able to show visually plausible motion sequences from just 4 Xsense accelerometers placed at the extremities. Deep Inertial Poser was one of the first to showcase a real-time deep learning-based pose estimation system, but they also use 6 professional Xsense IMUs. And most recently, Transpose and Physical Inertial Poser built on top of these findings and reported improved tracking results. However, these systems use somewhere between 4 and 17 professional-grade Xsense IMUs located in idealized locations like the ends of the limbs. And moreover, they use matched sensors with similar noise and performance profiles, which is very different from what we get from consumer-grade IMUs. So in IMUPoser, we have to deal with noisy data from mismatched low-cost IMUs. And the fact that the number of instrumentation points is sparse, not ideal, and also dynamic. And so overall, enumerating all of these unique body sensor configurations yields 24 different possibilities, with as little as 1 device and up to 3 devices operating concurrently. IMUPoser utilizes whatever subset of IMU data is available, potentially from just a single device, and produces a best guess pose. And here's a detailed look at our system architecture. So at first, our active device tracking system detects which devices are available and where they are located. This is done using a series of automated heuristics, like using the distance between the phone and the watch, and also the state of the IR proximity sensor on the phone. Next, unavailable IMU data is zeroed out in our IMU masking layer. And then this data is fed sequentially into our custom neural network, which is a bidirectional LSTM. which then finally predicts SMPL pose parameters theta. To train our pose model, we leverage AMAS, a collection of about 60 hours of motion capture data at around 120 frames per second to generate synthetic acceleration and orientation signals. As you can see, AMAS includes a wide variety of motions and activity sequences, such as locomotion, sports, dancing, and even cooking. We simulated 5 IMU locations as shown over here, and then we made 24 sets of simulated data, one for each of the 24 aforementioned possible IMU combinations, with missing IMU data replaced with zeros. And of course, synthetic IMU data may be different from real-world IMU data, and so we noticed that the noise profiles of the real-world and synthetic acceleration signals were the most different. Similar to previous work like transformer inertial poser, we decided to denoise both the real world and the synthetic IMU data with a moving average filter, and we found that this improved performance. We further fine-tuned the model to a small set of real-world IMU data from the DIP IMU dataset. And now moving on to evaluation. In order to compare prior work, we evaluated our model on the popular DIP IMU dataset. However, DIP IMU only consists of professionally grade XSense sensors, which is really not representative of the devices that people carry every day. As a result, we additionally created a new IMUPoser dataset, where we had participants wear or carry iPhones, Apple Watches, and AirPods as shown in the figure here, and they were also asked to wear 41 retroreflective markers to capture ground truth using a Vicon motion capture system. Then they were asked to perform a variety of motions, including upper body motions, lower body motions, locomotion, and even interactions. Full details are in the paper. And a comprehensive evaluation of the system can also be found in the paper, but let me just go over a couple of highlights. So here I'm showing how pose tracking accuracy varies across different body regions. This is a little bit complicated to take in at one go, so let me break it down. On the bottom, we compare various instrumentation scenarios, ranging from like no arm instrumented to either arm being instrumented. And on the left, we show mean per joint vertex errors in centimeters for different instrumented joints. So for example, in this bottom left corner, we compare left and right arm errors with different instrumentation scenarios of the arms, like the right arm being instrumented or just the left arm being instrumented, and so on. Results for the DIP IMU dataset are presented at the top, and then results on our IMUPoser dataset are presented at the bottom. We can first notice that the lowest error for a limb is when that limb is instrumented, which kind of makes sense. For example, averaging across both datasets, and with an IMU present on the right hand, the error is 14.6 centimeters for the right arm versus 21.6 for the left arm. Another interesting thing is that the lowest error is achieved when both the left and right limbs are instrumented. For example, with only one IMU on the arms, the error for both arms is around 18 centimeters on average. But whereas both arms having IMUs, the error is reduced to just 14 centimeters. An interesting exception to this is the legs. Unlike the arms, the legs tend to move in tandem, and this means that even one IMU on the legs is still highly effective at predicting both legs, and 2 IMUs really offers just a modest gain. But what do all of these numbers really mean? Here's a quick video just showing that. So here I'm wearing AirPods, an Apple Watch, and I have an iPhone in my right pocket. And on the right over here, I'm showing different simulated combinations of devices, ranging from just one device with the right pocket, all the way up to 3 devices. And as you can see, performance increases steadily as the number of devices increases. However, what's really cool to me is that even with just one device, the estimated pose is still pretty representative. And that's really where IMUPoser shines. We also open source our code and dataset. Check it out at the following link. Thanks, and see you around the conference.